Okay, problem 3-18. The total hip replacement is subjected to a force of F is equal to 120 newtons, and we have to determine the moment of the force about the neck at A and the stem at B. So I went and go ahead and I copied a really, really poorly drawn bare bone picture of everything they gave us, just to get something down to start working. The only equation you need to know for this problem is that the moment of a force, let me get my hand out of the way, sorry. The moment of the force is equal to the position vector from the point you're going to take the moment about to the force, and then cross that with the force vector of the force. So let me show you what I mean. We're going to start working on the moment about A. So let's go back to the better picture where you can actually probably see what I'm talking about. So we're going to get a position vector from A to the force, so that doesn't really give us much. It may be a little bit hard to see this, and I'm trying to figure out how to kind of goad you to see it yourself, but I think I'm just going to show you. So what I did is I drew a flat line from A directly across to the left to the line segment starting from point B going up to make a right triangle, because you see they give you separate measurements for 40 millimeters and 15 millimeters, almost like they wanted you to use 40 millimeters as a hypotenuse. And so that was pretty convenient. So I'll show you what I mean. I drew a separate picture down here. So you can see how I made that line to the left from A to the vertical line right there. So that gave us a right triangle with a hypotenuse of 40 millimeters, and then they gave us that the angle by A, it's 150. They gave us that the angle by B was 10, so that means the third angle by triangle geometry has to be 20 degrees. So we have a hypotenuse, we have an angle, we can therefore find sides. So let's find x and y components of this. So the x component of A, to the force, it's actually negative because it's going to the left. A is to the right of the force, but the force is to the left of A, and we only care about where the force is in relation to A. So the force is to the left of A. That means that your x component of your position vector is going to be negative. So the geometry of that ends up being negative 0.04, because 0.04 is 40 millimeters, but converted to meters. So negative 0.04 sine of, hang on, I am sorry, I just lost my train of thought. Okay, I figured it out. I'm sorry. I had copied down the wrong angle from my homework notes, and it was throwing me off. So the x component is negative 0.04 times the sine of 20. I have that up here. And then we can go back to the picture. The y, the force is above A, so that means your y component of that position vector is going to be positive. So it's 0.04 times the cosine of 20 over here. And that's a horizontal vector, force vector, so there is no k component to that vector or that force. So your k in your determinant is 0 for both r and f. So now we have r. I know you see that I have f. I'm going to show you how I got that. So let's go back to the picture. So this is our force vector right here. We have 120 pointing, I guess I could say that would be what, southeast, if we're going to be trying to give a direction to it. So 120 pointing right and down. Right and down means that your x component of that is going to be pointing in the positive direction. Your y component of that is going to be pointing down. So we have 120 and then an angle. 120 is our hypotenuse. So this the x component of that would be 120 sine of 15. Go ahead and put that right there. And then we have the y component, which is pointing down, so it's negative, is negative 120 cosine of 15. And as I said before, there is no k component. So we have our 3 by 3 determinant, and we can start doing our cross product. So taking I, we have zeros in k for both r and f, so our I component is going to be 0, and that's likewise for j. So we don't have to worry about I or j because k is 0 in both r and f. But when we do k, there are no zeros. So what we do is we multiply negative 0.04 sine of 20 by negative 120 cosine of 15. We get that sum, we get that product, and then we are going to subtract from that 0.04 cosine of 20 and 120 sine of 15. And that'll be our k moment. It's going to give us a moment of 0.418 Newton meters in the k direction. So that's our moment about A. Find the moment about B. We do exactly the same thing. We're just going to have different position vectors, but we'll have the same force vector because it's the same force. So let's look at where the force is in relation to B. Well, I see that the force is directly above B, so there is no I component to this. As you can see there is no I component in our determinant. But we have to find J, and that's a little bit tougher. It's going to be positive because we know that the force is above B. And as I know you can see, I used the sine rule, which simply states that the sine of alpha over the side A is equal to sine of beta over side B, which is equal to sine of gamma over side C. So I used sine of 150 over our unknown side is equal to sine of 10 over 0.055 meters, and I got 0.158 meters for our J on our unknown side. Stick that there, and then our force components are the same as in A. So we're going to do the same thing. We have zeros in K, so we know I and J are both going to be 0. And when we do K, we have that 0 in I, so it's going to be 0 times negative 120 cosine of 15. That's going to be 0. And we're going to then subtract 0.158 times 120 sine 15. And we're going to end up with negative 4.91 Newton meters K. And that's going to be our moment about B. That's all we needed to find, so we're done.